Welcome back. We have a bicyclist who is at rest fixing his tire and a friend riding by. And the friend riding by has a constant velocity. And as soon as the friend passes by, the bicyclist gets on his bike and accelerates at a constant rate of 2.8 meters per second until he catches up with his friend. And we have established the initial velocities of both, the accelerations of both, and we know the final velocity of the friend, but we don't know the time of either, and we don't know the displacement of either. And the question is going to be how long, or what is the amount of time that passes till the bicyclist catches up with his friend. Now, since we don't know the displacement or time for either, what we can do to get around that is to write two different equations that solve for what we do know for each rider, or that use what we do know for each rider, and solve for either time or displacement for both. And what that does is that enables us to find an equation for displacement of the rider, and displacement, there should be an X in there, of the biker, and set them equal to each other. If it doesn't make sense, it'll make sense in just a few seconds. So at the top here, I'm going to write an F for friend, and I'm going to write B for the biker. And what I'm going to do is I'm going to write an equation that solves for the displacement of the friend. Well, we have, what do we have with the friend? Well, we have the initial velocity, the final velocity, and we have the acceleration as well. So what we can do is we can take our fourth equation of motion, which is displacement is v initial times t plus 1/2 times acceleration times t squared equals displacement, right? That's going to be the displacement of the friend, F. But since the displacement of the friend is equal to the displacement of the biker, that is going to equal displacement of the biker. And now if we write an equation to solve for the displacement of the biker, what we can do is set the two sides of them equal to each other and ignore the displacement of both riders and wind up solving for t. So what information do we have for the biker, the bicyclist? Well, we have the initial velocity, we have the acceleration. We don't have the final velocity, though. That's okay, because we can use this exact same equation to solve for the displacement of the bicyclist. Our initial velocity, I'll write sub b there, plus 1/2 times the acceleration of the bicyclist times the time squared. Oh, what did I miss? I know what I missed. I forgot to put a t in there, didn't I? I'm thinking about writing this and saying this at the same time, and I missed something. This is t right here, right? Our initial velocity times t of the biker, which is the same thing as the friend, plus 1/2 times the acceleration of the bicyclist times t squared. Well, parts of this are going to cancel out already because, as I go back to blue here, we're going to find that some of these equal 0 and are going to drop out. For example, what's the initial velocity of the friend? It's going to be 4.5 meters per second times time. And at this point, I'm not going to write time B for bicyclist or time F for friend because they're both the same anyway. They're equal to each other. Plus 1/2 times the acceleration of the friend. Well, that's, I shouldn't have written the S there, or A there. I should have written what the acceleration is. What is it? It's 0. Times 0, that'll be easy, times t squared equals, we'll see how these two are equal to each other. Since the two displacements are equal, we can ignore them entirely and set the two sides of this equation equal to each other. That was the intent here, to solve for the displacements of both, which we know are equal to each other, and then set the two sides of the equation equal to each other. So this equals the initial velocity of the bicyclist, which is 0 meters per second, times time. Well, that'll be handy too because that'll drop out. Plus 1/2 times the acceleration of the bicyclist, which again, I wrote the A instead of the value. The value is 2.8 meters per second squared times time squared. You see how we set these two equations to solve for the same value, the displacement, but since the displacements are equal, we set the two sides of the equation equal to each other. And now all we're solving for is just time. We're going to know everything else. Well, right off the bat in red, I'm going to cross out those things that drop out. Look, that's a 0 right there, so that'll go away. And here's a 0 right there, so that will go away. So let's simplify this further. We have 4.5, and for the sake of simplicity, I'm going to break my own rule. I'm going to leave the units out. So we have 4.5 t equals, all the way over here, what's 1/2 times 2.8? Well, it's 1.4 t squared. All of a sudden, that boils down to be something very simple. Now that simple format there is going to be quadratic, but it's still a lot simpler than what we had before. So let's set this equal to 0. 1.4 t squared. And what we're going to do is we're going to subtract this 4.5 t from both sides, minus 4.5 t. And for clarity's sake, since remember our quadratic is ax squared plus bx plus c equals 0, I'm just going to put a 0 in there for the c as a placeholder, equals 0. So what's our value? What's our value for A? Well, our A is 1.4. Our B value is going to be negative 4.5, and our C value is going to be equal to 0. If you have the quad form equation, you can simply punch in those values for A, B, and C, and it will give you two answers. The correct answer is the one that is positive, because you can't have negative time. So our time is going to be equal to 3.214 seconds. That's the time that the bicyclist will take to catch up to his friend who has ridden past him at a constant velocity. Time of the bicyclist as well as the time of the friend.